So just like any other function, guys, I would like you to identify h and k. Now remember, h is always with x, whether it's inside a square root, up on an exponent. H is always with x. You always think opposite of what you see. The k is always at the end by itself, and you take it for what it is. Okay, so the h value of this guy is positive 1. You have to think opposite of that. Let me actually, yeah, this is better. H is positive 1, which means you're going to go 1 in the positive direction. The k value is negative 3, which means you're going to go 3 down. So once you identify h and k, what I like to do is box in the function ignoring h and k, leaving out h and k. So I really have this function y equals 4 times 2 to the x power. The a value is 4, the base is 2. Don't make the mistake of calling the base 8. The base is not 8, the base is 2. The a value is 4. So you're going to jump to a xy table, and you're going to plug in some inputs that are in order. So I always like to start with like negative 3, negative 2, negative 1, 0, 1, 2, 3, and so on and so on. And now let's actually plug in one number. The easiest number to plug in right here would be what? 0. What is 2 to the 0? 2 to the 0 is 1. Anything to the 0 power is 1. And then 1 times 4, or 4 times 1 is 4. So when I plug in 0, I get out a 4. And ladies and gentlemen, that's your first coordinate, right? Now, instead of plugging in 1 and doing the math, instead of plugging in 2, right, plugging in 2 right here and doing the math, instead of plugging in 3 and 4 and plugging in negative 1, negative 2, all that fun stuff, instead of doing that, let's use the base, which we know is 2, to get our following outputs. Now we're only going to be able to do this because I put these inputs in order. If the inputs were not in order, we would not be able to do this. So 4, the output 4, if I were to multiply it by the base 2, what do I get for the next output? 4 times 2 is 8, and then times 2, 16, and then 32, and then 64. See how easy it is to come out with these coordinates? Going backwards, if you're multiplying by 2 going this way, and the only reason we're multiplying by 2 going this way is because of the base 2. If the base would have been 3, then you'd be multiplying by 3. You'd get 4 times 3 is 12, times 3 is 36, but the base isn't 3, the base is 2. So you're multiplying by 2 going this way, which means backwards is dividing by 2, or multiplying by half. 64 divided by 2 is 32, divided by 2 is 16, divided by 2, divided by 2, divided by 2 is what? 2, and then 1, and then 1/2, and then 1/4, and then 1/8, and then 1/16, and then 1/32, and then 1 over 64, and 1 over 128. And 1 over 128 is almost nothing. So we know that it infinitely gets close to 0. So we could even talk about end behavior if you wanted to by analyzing this input-output table. As your x's go to positive infinity, your y's go to positive infinity. As your x's go to negative infinity, your y values go to 0, because it keeps getting smaller and smaller and smaller, but not negative. It keeps getting closer to 0. So let's graph these coordinates right here. We have, so far we have 0, 4, 1, 8. We have negative 1, 2, negative 2, 1, negative 3, and then half. So this is where we keep going half, right? Going backwards, it's half. So you got half right there, and then you have half of the half, which is right there, and then half of the half, which is right there. And it, at this point, looks like it's actually touching. You could actually draw it on it if you want, but you know it never actually touches. It just infinitely approaches. Okay, so, but we don't want to actually draw it because this isn't our actual graph. We still need to consider our h and k shift. So on each one of these, you're going to want to move each coordinate 1 to the right and 3 down. So if you go 1 to the right, 1, 2, 3 down, you'll end up right here. 1 to the right and 3 down, 1, 2, 3, right there. And move this up. 1 to the right, 1, 2, 3, right there. This guy, 1 to the right, 1, 2, 3, right there. And what I like to do also, instead of doing the other coordinates, I like to go to the asymptote, to the value it infinitely approaches. We know that the blue dots infinitely approach 0. So if you get this line and just shift it 3 down, because that's your k value, 1, 2, 3, this is a new infinitely approaching line. Okay, so it's actually, you could draw it like if it's actually on it, even though you know it doesn't actually touch it, just infinitely approaches. And there's your graph. Now let's say you did happen to mistakenly draw your parent graph. Whoa, that's ugly. Mistakenly draw your parent graph. Then what you could do is just put a couple of X's on it. That way I know that that's not your final graph. The other one is. Okay? So on exponential decay functions, the base will be less than 1. So maybe we should start out with something like this. Just asking you, why? That is disgusting. Why? That's still ugly, but who cares? Base 1/2 to the power of x. That's a decay function. Why is it a decay function? Because the base is less than 1. Okay? So if the base is less than 1, it's going to shrink. If you multiply any number by a value less than 1 but greater than 0, okay, so by a fraction that's less than 1 but greater than 0, it's going to shrink. What's 20 times half? It shrinks to 10. What's 20 times 1/4? It shrinks to 5. So any fraction that's less than 1 but greater than 0 is going to cause it to shrink. Now what that looks like from left to right is that it's a great value and it shrinks to nothing. Okay? Now, if you compare that to y equals 2 to the x, and that's a growth function because the base is greater than 1. Okay? So it's going to grow from left to right. So from left to right, it's going to grow. Okay? So we need to understand the difference between decay and growth. Okay? Ladies and gentlemen, is that a decay or growth function? Decay or growth? It's growth. Why is it growth? Because the base is greater than 1. Now, what if I had a negative sign in front? Would that be a growth or a decay? It's still a growth because the base is still greater than 1. That negative sign in front is your a value being -1. And we know, okay, so if a growth function originally looks like this, growth, the negative sign in front, the a value being -1, all that would do is cause a reflection. It's a growth in a negative direction, okay? Now, you're probably thinking, what? What do you mean a growth in a negative direction? It makes total sense. Think about this. Let's say you had a savings account, and at first you didn't have any money, and you started saving money, and then all of a sudden what happens? You have a lot of money, right? That's a growth in a positive direction. Now, the red one is still a growth. I know you're probably thinking, wait, how's that a growth? It's going negative. Well, think about you have a bunch of credit cards. You don't owe any money, but you go shopping, and then you start spending money. What happens? You grow in debt, but in the negative direction, right? So there is such thing as growth in the negative direction. That's when your a value is -1. But nevertheless, the base is still greater than 1, which makes it a growth function, whether the a value is positive or negative. Growth or decay? Growth. Hey, but that's a fraction. Oh, did I just... Sorry. Growth. Sorry. Going through puberty. That's a growth function. Why is it a growth function? Base is greater than 1. Okay. Growth or decay function? Decay function. Why? Because the base is less than 1, smaller than 1, right? Growth or decay function? Decay. It's decay. Oh, but what about this huge 935? So what? The base is still half. It's still going to decay. From left to right, it's going to go down to nothing. I think we got the idea here. So let's jump to graphing the simplest type of decay function, which is y equals 1/2 to the x power. So what should we do? That's how to start it. And the inputs, what are you going to use as inputs? Okay, if you're going to use 0, put that in the middle so you could have space for negative numbers. 0, 1, 2, 3, -1, -2, -3. The key is consecutive order, consecutive integer inputs. Nice and in order. Now, when we normally graph other functions, yeah, you could plug in a 0, plug in a 3, plug in a -5, whatever you want, but those aren't in order. You want these guys to be in order. That way you could use the base to find the pattern of the outputs because the inputs are in order. So let's plug in one simple number like 0. Plug in 0 right there. What's 1/2 to the 0 power? That is 1. And now from this point, from this output 1, Hayden, what I could do is stop texting and start multiplying the base by half, right? So I could go 1 times half and get 1/2. And I could go half times half and get 1/4. Then 1/4 times half and get 1/8. And I could keep going. The input 4 will give me the output 1/16. The input 5 will give me the output 1/32. 1/32, if you divide it out on the calculator, it's really close to 0. But then again, you could keep going, and it'll be 1/64, and then 1/128, and it gets closer and closer to 0, but you'll never actually get there. So as you go down, you're simply multiplying by the base, which is half. 1 times half, times half, times half, times half. As you go backwards, you're going to be dividing by half, which is really multiplying by the reciprocal, which is really multiplying by 2. In other words, 1/8 times 2 is 2/8, which reduces down to 1/4. 1/4 times 2 is 2/4, which reduces down to 1/2. 1/2 times 2 is 2/2, which reduces to 1. 1 times 2 is 2, and then 2 times 2 is 4, 8, 16, and so on and so on. And we could graph this now, right? Go for it, graph it. So 0, 1 is right here. 1 and 1/2 is right there. And you know what? Let's zoom in because we're going to keep going. As we go in the positive direction on the x's, you're going to get half, you're going to take half, you're going to take half, and half, and half, and it keeps getting smaller and smaller. So I'm zooming in here. That's half of that. That's half of that. At this point, it looks like it's touching. You could draw it like if it's touching, but you know that it never actually touches, just infinitely approaches. And as you're going backwards, it's kind of like doubling, right? So -1, 2, -2, 4, and so on and so on. -1, 2 is right there. -2, 4 is right there. -3, 8 is way up there. And -4, 16 is off the graph. So is there an H and K shift on this guy? No. So I could graph it. Here we go. Graphing. Actually, let me use blue. Graphing and infinitely approaching. Arrow right there, arrow up here. Let's talk domain and range. Domain. What are the domain values? What are the domain values, guys? What are the x values? All real numbers. You could see that on the XY table. You know you could go -3, -4, -5. You could keep plugging in all infinite amount of negative numbers. You could plug in infinite amount of positive numbers. So domains x equals all real numbers. Now the range are your y values, and y is up and down. So where is this graph right here anywhere down here on the negatives on the y? No, it's all up here, right? So y is what in terms of this graph? Greater than 0. And again, the most common mistake, greater than or equal to, but we know, even though it looks like it touches, we know it never actually touches, so you cannot put the or equal to. It's just greater than 0. It'll always be greater than 0.